Hello! In today's pre-lecture video, we're going to be talking about enthalpy of reactions. We're going to be looking at calorimetry. We're going to look at Hess's law. We're going to look at standard enthalpies and bond enthalpy problems. So we're going to start out by looking at enthalpies of reactions. And we would write this as delta H Rxn, enthalpy of your reaction. And it's generally when we look at the enthalpy of a reaction, such as for this one right here, we have methane gas plus oxygen gas goes to carbon dioxide gas and 2 water molecules. This is just a simple combustion reaction. But it has a delta H of reaction equal to negative 800. Sorry, one second. Delta H of reaction equal to negative 890 kilojoules. So that's saying that for this reaction as written, it's going to release 890 kilojoules. So it'd be for 1 mole of methane reacting with 2 moles of oxygen gas to produce 1 mole of carbon dioxide and 2 moles of water. Now, that is the reaction written in the forward direction. If we were to write it in the reverse direction, CO2 gas plus 2H2O liquid goes to CH4 gas plus 2O2 gas. This would have a delta H of reaction equal to positive 890 kilojoules per reaction. I'm just going to write it like that. Okay? So the forward and the reverse enthalpy of any reaction is just going to be the opposite sign of the other direction. And we'd also write our delta H of reaction is equal to our products, our enthalpy of our products, minus the enthalpy of our reactants. Okay. So as we have our reaction, as I said, it has to be as written. Whatever we write, that's what our delta H of reaction is going to be. So, some facts about enthalpy. So, some better understanding of it. It is a state function. It only matters about the beginning and end states, such as reactants and products. It doesn't matter how we get to those. It's extensive. It's an extensive property. So we'll always see it as a kilojoule per mole or a kilojoule per reaction, right? And then the sign of delta H in the forward direction is equal to the negative of the delta H in the reverse direction, but they are going to have the same magnitude. Just a different sign. Okay. And delta H depends on the states. If you change your state, it's not going to have the same delta H. So pay attention to those states. Okay. And that should make sense. It should take different amount of energy to get between the gaseous state and the liquid state. So let's actually try this. So we have that methane reaction, the combustion of methane. And as I said, this has a delta H of reaction equal to negative 890 kilojoules. Let's move this a little bit. Kilojoules per reaction. So as written. So like so. So for every 1 mole of methane, 2 moles of oxygen, or 1 mole of oxygen, 1 mole of methane, 2 moles of water. Oops. Let's try that again. There we go. So as written, it's 890 kilojoules per mole released, so a negative. So let's say we have 25.8 grams of methane. We want to know how much energy will that release? How much energy will that release when combusted? So we want to know how many grams of methane, or with this many grams of methane, how much energy you're going to release. So as written, for every 1 mole of CH4, we produce 890 kilojoules of energy. Okay. So the first thing we want to do is convert that from grams of methane into moles of methane. So we have 25.8 grams of methane. Methane has a molar mass of 16.043 grams. So when we divide that out, we get 1.6125 moles of methane. And we see this is greater than that 1 mole, so that we're going to release more than 890 kilojoules. So 1 mole of methane produces negative 890 kilojoules of energy. So we will get negative 1,435 kilojoules, and with correct number of sig figs, negative 1,400 kilojoules of energy will be released when 25.8 grams of methane are combusted. Okay, next thing we're going to be looking at is calorimetry. Calorimetry is the measure of heat flow. So we're going to be looking at a closed, or as close to a closed system as we can. So we enclose a system. So we're trying to isolate. So we enclose the system in an insulated container. And then look at the heat absorbed or released by the system. Okay, so a very common one here is a coffee cup calorimeter. And in a coffee cup calorimeter, we have 2 coffee cups kind of nestled within each other, so that we get some insulation. And then inside we have a thermometer, and we have right here is our system. And sometimes it's a system plus surroundings if you've got an aqueous. So this is usually an aqueous reaction. So you've got some aqueous reaction going on, and that aqueous reaction's temperature change is going to be observed on the thermometer. So what we're looking at with a coffee cup calorimeter is we're looking at the delta H for that reaction. Okay. So we call this coffee cup calorimeter a constant pressure calorimeter. Okay. And with this constant pressure calorimeter, our heat is kept at a constant pressure, and when that is true, it'll be equal to our delta H. So within these reactions, we're actually going to be looking at this and equating it to this using the following equation. So Q is equal to mass times by specific heat times by delta T. So our Q is our heat here at a constant pressure. And if we're at a constant pressure, our heat is equal to our enthalpy. All right, so we don't have any change in that. So here, we also have M, which is our mass, and then CS is specific heat, and our delta T is our change in temperature. So what happens is we have a substance, a reaction going on within our coffee cup, and as we have a specific mass of that, because enthalpy is extrinsic, so it depends on the mass. So we have some mass of that. It's going to react and it's going to change temperature. As it changes temperature, we're going to look at how much heat it is based on what its specific heat is. Okay, so our mass is going to be in grams. Our specific heat is going to be joules over grams times by degrees Celsius, or joules over grams times by Kelvin, where degrees Celsius, our delta degrees Celsius will be equal to our delta Kelvin, so they're interchangeable. These are equivalent. And then our delta T can be either degrees Celsius or Kelvin, again, because that change in the temperature is going to be the same whether you have degrees Celsius or Kelvin. Okay. Now, generally, as I said, we're looking at a aqueous solution, so we're actually going to be looking at our water changing temperature. So we'll look at Q of our solution is equal to the mass of our water times by the specific heat of our water times by delta T, change in our water. And what's going to happen is our reaction is going to go, it's going to have a temperature change, and that temperature change is going to, or the change in energy is going to be absorbed by our solution, or our water. And we can look at how much energy the water has absorbed or released. Generally, we're looking at the water absorbing heat. So almost always the delta T for this reaction is going to be positive. After we figure out how much heat, so this tells us how much heat the water absorbs, we can then relate it back to our substance itself. So our Q of our solution will be equal to the negative of the Q of our reaction. So after we figured out our Q of our solution, we can then put it in here, and we know that the negative value of that will be our Q of our reaction. And then once we have our Q of our reaction, we can put it into mass of our reactants, or reactant, times by the specific heat of our reactant, times by the delta T of our reactant. Okay, which oftentimes is the same as the water. We also have what's called constant volume calorimetry. And this is going to be what's called bomb calorimetry. And that's exactly what it is. It's a bomb. So you've got a insulated box, and in there you've got a little sample cup, and that's where you actually have your sample, right? And then the entire thing is filled with water. So your reaction is separated, but it's going to be releasing heat to that water. And this is almost always combustion reactions. So you've got a way of actually causing an ignition in here. So these are ignition wires. So you're going to ignite your sample, and then that sample is going to burn, and you can actually look at the temperature change of your water. Okay. So here, since we have constant volume, our delta E is going to be equal to our Q at a constant volume. So now we're looking at our internal energy instead of our enthalpy. And what we get is this is generally used with a standard first and then used on other reactions. So you get your Q of your reaction is equal to the negative C of your calorimeter times by your change in temperature. So this is determined using a standard. So something they already know the temperature change of. So you're going to be using this in conjunction with Q of your solution is equal to mass of your water times by the specific heat of water times by your delta T of your water. So each of these will be used together. Okay. Generally we use CS, our specific heat, in these equations. But we can also use our molar heat capacity. Which is just going to be a different unit. So specific heat is joules per grams times by degrees Celsius. And then our molar specific heat is joules per mole times by degrees Celsius. So it's the same idea. So if you're using molar heat capacity instead of specific heat, your reactant your equation becomes this. So you just change your unit from grams of water into moles of water. just as a note, one of the specific heats you're going to use the most is of water. And it's 4.184 joules per grams times by degrees Celsius. This will be given, but it's good to keep it in mind. Next topic for this lecture is Hess's law, one of my personal favorites. Hess's law takes advantage of the idea that enthalpy is a state function. So remember that enthalpy is a state function. And because it's a state function, we can use enthalpy of a series of steps to kind of add them together to get one reaction. So we're doing a reaction in a series of steps. And we combine those steps to form an overall reaction. And we combine the reactions themselves to get an overall reaction, just like we did when we were looking at balancing redox reactions. We combine those reactions and we get an overall reaction, but we also combine our enthalpies. So I think that the easiest way to look at this is just to do a reaction, an example of this. So we have what I'm going to call our target reaction, which is C solid plus water goes to carbon monoxide gas plus hydrogen gas. So this is a reaction we want to figure out the delta H of. Okay? And using Hess's law, we can use other reactions that combine to produce this overall reaction and their enthalpies to determine it. So we have a set of given reactions, such as C solid plus O2 gas goes to CO2 gas, and that has a delta H of negative 393.5 kilojoules per reaction. And then we've got another one, 2 carbon monoxide gas plus oxygen gas goes to 2 carbon dioxide gas molecules. Delta H of reaction equal to negative 566.0 kilojoules per reaction. And then lastly, 2H2 gas plus O2 gas goes to 2H2O gas, negative 483.6 kilojoules per reaction. So we want, using these three reactions, we want to come up with this reaction. Remembering that anything that's on the same side of the reaction is going to combine, anything that's on opposite sides of the reaction are going to cancel out. Some things to keep in mind as well. If you flip an equation, so you do the reverse of the equation, you also flip your enthalpy. If you multiply your equation by 2, you multiply your enthalpy by 2. So its forward reaction is the opposite side of its reverse reaction for enthalpy, and it is extrinsic, so it depends on the amount. So if you multiply the whole thing by 2, you need to multiply your enthalpy by 2. Okay, so I like to look when I'm trying to figure out these types, and I like to make sure that I have my products and reactants on the correct side. So this one is a product, this one is a product, and then we have H2O there's a reactant and reactant, and then right now it's a reactant and a product. Then on our other side, we have carbon monoxide, H2, H2. So currently, this is written the correct way, this is the opposite way, and this is the opposite way. Also note that we want one carbon monoxide and one H2 gas, but we have two here and two here. So watch what I do. I'm going to leave this equation as is, the first one, because it's written correctly and it has the correct number of moles of carbon solid. The next one, I'm going to flip the equation and divide by 2, because I need that carbon monoxide to be a product and I only need one of them. And then for the last reaction, I'm going to do the same thing. I'm going to flip the reaction so I can get that H2 on the product side, and I'm going to divide by 2 so I only have one H2. So I'm going to have C solid plus O2 gas goes to CO2 gas, giving me a delta H of negative 393.5 kilojoules per reaction. Then flip and divide by 2. So this gives me CO2 gas goes to CO gas plus 1/2 O2 gas. And whatever I did to my reaction, I do the same thing to my enthalpy. So I flipped it, so I give it the positive sign and divide by 2. And then the last one, we get water going to H2 gas plus 1/2 O2 gas. Flip the sign and divide by 2. And when we combine these, we'll also combine these, and we get our CO2 is on opposite sides, so they'll cancel out. Our O2s are on opposite sides. There's one on the left side, 2 1/2s on the right side, so they'll cancel out. And then everything else should stay as is. So we get C solid plus H2O gas goes to CO gas plus H2 gas. And if we look up here, that is what we are supposed to have. Fantastic. And then we combine our delta H values. And when we do that, we get 131.3 kilojoules. And that's it for Hess's law. You're just going to manipulate equations to try and get to a desired equation. We can also look at enthalpy of formation. So here we're looking at forming a compound from its elemental substances. So from atoms or molecules in their elemental state. So it's very important that you remember your diatomics here, right? So you should know at this point what your elemental forms are, especially for carbon, hydrogen, and oxygen. Those are going to be the most common that we're going to be using. All of your metals, they're just going to be monoatomic metals in the solid state, with the exception of mercury. Carbon is just going to be carbon solid, hydrogen gas, oxygen gas, nitrogen gas, chlorine gas, bromine liquid, iodine solid. Those should all be things you should be able to come up with. Fluorine gas. So make sure that you review those diatomics if you're not sure. So let's say, and this is going to be a standard enthalpy change. Which means that it's going to be done at 25 degrees Celsius and 1 atmosphere. So we're going to denote that as delta H naught. So that little naught means standard. And it's going to have a subscript F for formation. Okay? So let's say we want to form C2H5OH. So this, if we look in a table, so this would be a value that would be given in a table, we get negative 277.7 kilojoules per mole of ethanol that's produced. So what we see is this is our heat of formation for this substance. This is how much energy is released when we form ethanol. So because it's a heat of formation, we're going to form it from the elemental compounds. So we have carbon solid plus hydrogen gas plus oxygen gas. So these three substances, because it's carbon, hydrogen, and oxygen that form it, will form 1 mole of our liquid ethanol. Now, it is not balanced, and that's what we need to do next, keeping in mind that this is for 1 mole, so we will keep this as 1 mole. So if we have 2 carbons on our right side, we'll put a 2 right here. We have 6 hydrogens, so we'll put a 3 right here, and we have 1 oxygen. To get to 1 from 2, we have to divide, so it would be 1/2. And now that we have this heat of formation equation, let's give ourselves a little more room. We can use this type of equation within our Hess's law as well. Okay? So that is everything I have for you. We will do lots of practice problems on these in class. Should be fairly simple and fun. We'll also very briefly talk about energy and food. Let me just talk about it now. Sorry, I lied. We're going to talk about energy and food real quick. So we have food contains or has potential energy that once digested converts into kinetic energy. It is oftentimes then also converted back to potential energy when it's stored as things like ATP. Sorry. So it goes from potential energy to kinetic energy to potential energy again. But each macromolecule has a different amount of energy per mass. So macromolecules include fats, proteins, and carbohydrates. Our fats give us 9 kilocalories of energy per gram, where 1 calorie is equal to 4.184 joules. and 1 kilocalorie is equal to 1,000 calories. And then 1 big C calorie is equal to 1 kilocalorie. So this is what is on food labels. Okay, proteins and carbohydrates both have 4 kilocalories per gram. Okay. So that really is it. So that is all for today's pre-lecture video, and we will do lots and lots of practice on this when we get into class. Bye, everybody.